This is a simulation of Scientific Data Systems 910. The 910 was the first silicon transistor machine that was available. It came out in the early 60s. It was a 24-bit computer, binary computer. And everybody thought of it actually as an octal machine. The 24 bits were grouped into 8 groups of 3 bits each. Each octant could take the values 0 through 7, hence 8, octal. The simulation shows the instruction counter, the instruction register, the A register, the accumulator, B register, an extension, which is just used in this program as a display, the index register, which is used quite a bit in this program, the pot catcher, which is a display register, the effective address register, and the result. This shows the result of the program that the computer is running, which in this case is a translation of binary numbers to binary coded decimal numbers, and you can see the result being built up. Now I'm going to stop it. It was running at about 5 instructions per second. It was artificially slowed down. It runs, if it's not slowed down, it runs at about 4,000 SDS instructions per second. So I'm going to single cycle through to where we get to the top of the program, which is, there's an escape. Okay, memory increment, we're going to go on to the next value. So the next value that we're going to convert is 314,170. The last value was 314,169. Okay, increment, skip on negative. That was to test to see if the program was altogether done and had converted every possible value from binary to binary coded decimal. 24-bit machine, 23 bits plus a sign. It's about 8 million is the decimal equivalent of the biggest number that can be represented, plus or minus 8 million. So, okay, there's a branch unconditional. Okay, here's the top of the program, load A. So the first thing we're going to do is fetch the operand, fetch the argument, which is the octal equivalent of 314,170. You do a branch and mark place, which is a subroutine call. Typically on the 910, the argument to a subroutine was always in the A register. What this subroutine is going to do is convert this binary octal number to binary coded decimal. The results are going to appear here. Each of these, this is million, 100,000, 10,000, thousand, hundreds, tens, units. Each of these digits is a separate word. Okay, so we do branch and mark place to the top of the subroutine. First thing the subroutine does is store the input argument. Load X with -7. So what we're going to do is we're going to zero out all the result. Okay, register change. This register change is going to copy the A register into the B register, and at the same time clear the A register. And now we're going to do an index store A. The index, here's the tag field 2 in the instruction. The index says add the contents of the index register to the address field of the instruction and use that as the effective address, which is going to be 400. and that's going to zero the millions field of the result, which happens to already be 0. Okay, BRX is going to increment the index register and branch back to the store A instruction. Okay, index store A, now we're actually going to do something. This 3 is going to change to a 0. BRX, okay, now we're just in a tight loop, zeroing out the results. And BRX this time, the BRX is going to fall through. We do a load A to restore the input argument. There's a no op because I had an extra instruction in there. Okay, load X with -7, we're going to convert up to 7 digits. This parallel output is going to take the effective power, the current power of 10, which turns out to be 1,000,000, and send it to the pot catcher. This is the octal equivalent of 1,000,000. Okay, now we're going to subtract that same value from the input in the A register. It's the way the binary to BCD works, by repetitively subtracting out powers of 10. First power of 10 that we use is 1,000,000. The A register went negative because we couldn't subtract 1,000,000 from 300,000. We could, but there wasn't. It went negative. So now we do a skip on greater, and this is the operand of this instruction is -1. So it skips if the result is 0 or positive, which meant that the subtract was able to take place. And we're going to see here that we do not skip. We branch down. This is a restoring add. This adds 1,000,000 back in, and BRX is going to change the index register, and we go, and the effective address is now going to point to 100,000. This is the octal equivalent of 100,000. Okay, now we do the subtract. A did not go negative. Skip on greater. This is going to skip. Memory increment. We're going to increment the 100,000 field and branch back to the subtract instruction. Do another subtract. Skips. Memory increment. Branch back. This is the 4-instruction loop. Subtract. Skip on greater, memory increment, and branch. Now this time, when we attempt to do the subtract, the A register is going to go negative. There were only 300,000s in the input argument. You subtract, A goes negative. Skip on greater does not skip. We branch down to a restoring add. Put that back, and increment and branch on the X register, and now we're going to do 10,000. This is the octal equivalent of 10,000. Subtract, I think we're able to do that once. Memory increment, 310,000 so far. Branch back to the subtract. This time it goes negative. Do not skip. Restoring add, BRX. This time this is 1,000. This is the octal equivalent of 1,000, and we're able to subtract that at least once. Memory increment, there was 311. Branch back, subtract, it skips. Subtract, it skips. Subtract, it skips. Memory increment for the last time for the 1,000 value. Branch back, attempt to subtract, goes negative. Restoring add, BRX, And now this is the octal equivalent of decimal 100. Do a subtract, we can do that probably just once. Subtract again, goes negative. Restoring add, BRX. We pot this time, this is 10, so we'll be able to do a few tens. You can see the tens accumulating. Increment, subtract. Okay, that time it went to 0, so we're still going to skip memory increment. 314,170 branch. Subtract again, it goes negative. We do a restoring add, which really doesn't do anything. Then we're going to do 1. We're going to try to do 1, but there are no 1s left in there. Skip on greater. Restoring add goes back to 0. BRX. Okay, so there's the final result, 314,170. Branch return goes back to the main program, which is at 200. And escape is a, this compares the results here with what the input argument was. Memory increment, and here's a load A with the octal equivalent of 314,171. And now I'm going to let it run. You can see the result being 0, and now you can see the result being built up for the 314,171. Now it's being zeroed, and now it's going to do 314,172, and so on, up to about 8 million. Thanks for watching.